All right, so today we are going to continue talking about concept to thermal activation. So let's first talk about the thermal bimorph principle. So I am going to focus on bimetallic strips, so only two materials, because my brain can't comprehend the math that goes in when there's more than two materials. So let's say that we have a beam like so, and this beam is made of a particular material. So let's call this E2 and alpha 2, where alpha is the linear coefficient of thermal expansion. And then on top of this beam is another smaller beam. And the second beam has a Young's modulus E1 and a linear coefficient of thermal expansion alpha 1. And we have an anchor point over here on the left. And let's say that the length of these beams are L, and they're having the same length. So when the two different materials, or excuse me, when the two materials have different coefficients of thermal expansion, so alpha 1 does not equal alpha 2, when they are heated, they are going to want to expand by different amounts, right? So the section on top, let me do this in a different color. Oh, I can't see it because it's behind the zoom thing. Is going to have a length that will be L times, or lowercase l, excuse me, that's what I was using. 1 plus alpha times the change in temperature, alpha 1 times the change in temperature. And this one on the bottom will expand by an amount 1 plus alpha 2 multiplied by our change in temperature. And if the alphas are different, then obviously these lengths are different. So what's going to happen? Well, we're going to see that our structure is going to bend, and it is going to bend towards the material that has a lower coefficient of thermal expansion, right? So looking at it strictly from a side view, let's say that we are at some equilibrium temperature. T is equal to T naught. In this equilibrium temperature, our beams have the exact same length. So here we have, if I could draw a straight line. Our first beam, here we have our second beam, right? This guy up top has alpha 1, this guy down here has alpha 2, and let's say that alpha 2 is less than alpha 1, then at some new temperature, T naught plus some alpha T, what we're going to see is beam bending. because our total length here has increased by some small amount. L times 1 plus alpha 1 delta t. And our total length here has increased by some small amount, L plus alpha 2 times delta t. And these two lengths are unequal. So the fact that the two materials are bonded together tightly causes a curvature. All right. So for a uniform temperature change, delta t, the beam curves and assumes the shape of an arc. So effectively, the amount of bending is distributed, or the deformation is distributed along the entire length of the beam structure. Okay. With length L. The radius, let's call this capital L, because there is expansion that's happening. The radius of curvature of the arc is given by the following relationship. So 1 divided by the radius of curvature. This is going to be a heck of a fraction. So in the numerator here, we're going to have 6 times the width of material 1 times the width of material 2 times the Young's modulus of material 1 times the Young's modulus of material 2 times the thickness of material 1 times the thickness of material 2 times the sum of the thicknesses times the difference in coefficients of thermal expansions times the change in temperature. So that's our numerator. And then our denominator is the width of material 1 times the Young's modulus of material 1 times the thickness of material 1 squared. That whole quantity is squared. Then we have the exact same thing except relating to material 2. So the width of material 2, Young's modulus of 2, thickness of 2 squared, that whole thing squared. And then we have our cross term. So this is twice the width of 1, the width of 2, Young's modulus of 1, Young's modulus of 2, thickness of 1, thickness of 2, times twice the thickness of 1 squared, plus 3 times the product of the thicknesses, plus twice the thickness of 2 squared. So we have this horrifyingly long, ugly equation for the radius of curvature because of the rectangular geometry that we have in this system. Okay. So luckily for us, the angle of the curvature is trivial because we're dealing with an arc length, right? So arc length is just radius times angle. And so we're going to use the invert of that relationship. The arc angle is just theta will be equal to our length divided by the radius of curvature. And so using this and a little bit of trig, we can figure out what the vertical displacement of the free end of our beam is, right? So the situation that we are describing, and this is going to be vastly exaggerated because we should see that the angles that we're going to wind up getting are pretty small. So here's our anchor point. And this horizontal line here represents the beam effectively at rest or not undergoing any expansion or anything like that. And then this line right here represents it after it has curved due to thermal expansion of the bimorph. So this distance is R, this distance is R, and this angle right here represents theta. This vertical displacement D is simply going to be R minus R cosine theta. So that represents the vertical displacement experienced as the beam bends due to thermal expansion. Okay. So let's put this into practice and look at an example problem. Where things are made slightly more difficult, but we'll talk our way through it pretty trivially. So let's say that we have a bimetallic cantilever beam. Is made of 2 layers. Having different lengths. So from a side view, we're going to have our bottom beam. So let's say that this has Young's modulus E2, thermal coefficient of expansion alpha 2, and we have a total length of L2. And then our first material will be over here. Young's modulus of E1, thermal coefficient of expansion alpha 1, some length L1. From the side, or actually from, I guess, a front view, because that was a side view. Here is our material 1. So this is E1 and alpha 1. We have a width. Sorry, this should be 2 because we're doing the bottom thing. My apologies for messing up those subscripts. And some thickness 2. And then on top, we have some width W1, because this material has Young's modulus E1, thermal coefficient of expansion alpha 1, and the thickness T1. And let's say that L1 is 100 microns, L2 is 200 microns, thickness of layer 1 is half a micron, thickness of layer 2 is 1 micron, and the widths are going to be equal, 20 microns.
You're right,
Thank you. Thank you very much, Hayden. I would not have noticed that. So let's say that material 1 is aluminum. Aluminum has a Young's modulus E1 of 70 gigapascals and a thermal coefficient of expansion that is 25 parts per million per degree C. Material number 2, silicon nitride. Young's modulus of 250 gigapascals. Coefficient of thermal expansion 3 parts per million per degree C. If the beam is straight, at room temperature, determine the vertical displacement of the free end of the beam due to a temperature increase of delta T is equal to 20 degrees Celsius. So I want to draw the situation that's happening here so we're all on the same page. All right. So I'm going to draw the long beam on top, like so. And then here is our shorter beam, right? So this is our situation. Our displacement is going to be expected to be up with this particular view of it because the long beam material has a smaller coefficient of thermal expansion. So effectively what we're going to see is that the bimetallic material is going to have some radius of curvature, R, and some arc angle of theta. So let's call this from point A to B. And then our beam end, let's call it point C. And so it's not from the segment from B to C is not going to experience bending because there's nothing there to bend it. It's just going to follow that length, right? Or that arc. So something, just a straight line like so. So here is point C. So we have some displacement out to point B, and then some total displacement out to point C, right? Well, so far we know, or we've been given equations to figure out what that displacement at B is. So how are we going to tie that to our displacement at C?
Well, we find the slope where it is at B. And imagine that involves the tangent function.
So
And then we multiply that by the length of the one.
I argue that angle right there should be theta as well. And then we can just use simple trig, right? So DC should just be DB plus L2 minus L1, which is the part that isn't undergoing bending, times the sine of that angle theta. Anybody not following my trig? All right. So working with this, our radius of curvature is given by that terribly long equation. I'm not going to bother writing it down, and I'm not going to make you guys plug in the numbers. we wind up getting 260.9 per meter. From this, the radius of curvature is 3.83 millimeters. Theta is then L1 over our radius of curvature. Which comes out to be 0.026 radians or 1.496 degrees. Our displacement at point B is just R times 1 minus cosine theta. So that's plugging in that 3.83 millimeters for R and that 1.496 degrees for theta. This comes out to be 1.305 microns. And then our displacement at C is just our displacement at point B plus, as we mentioned above, L2 minus L1, where we're using the difference in lengths because this is a part that represents not bending. Sine theta, and this comes out to be 3.916 microns. Okay. So this bimetallic or bimorph effect gives us lateral displacement. Okay, so our beam is out in a longitudinal direction and we're not getting extension in the longitudinal direction. We're getting displacement that is effectively orthogonal to the longitudinal axis of the beam. So what if we wanted in plane displacements instead of curving into or out of the plane? What if we wanted a displacement in the plane? So to get that, we're going to look at single material thermal actuators.
Let me just ask, you mentioned not wanting to discuss more materials, but could you keep the same route you had? For instance, you have your top beam, which is smaller. What if you had another beam underneath the long segment with equal properties? So you have two sandwich beams with one in the middle, their expansion rates are the same, this one expand, wouldn't that allow it to also extend, but it'd be a trimorph, I guess?
So the more materials we put it, so I'm not, let me try to draw and we'll make sure that we're talking about the same thing here. So this is a tangent, but let's see.
Sorry.
Yeah, no, not a problem. So you're saying I have a beam here. This particular beam, let's call it 1 for now, has a particular Young's modulus and a particular coefficient of thermal expansion. Then we put a material on top. Does the material on top cover the entire length of the beam or just some portion of the length?
Just some portion.
Yeah. So let's put a material on top here. Let's call this E2. With some altitude. Now you are suggesting I put a third material on top, or a third layer on top.
A third layer underneath. So underneath that beam with equal properties to one on top.
Same length as the one on bottom?
No, same length as the one on top.
Okay,
I'm just asking if whatever bending you might get from the two dissimilar metals, if there was another one sandwiched underneath.
so you're saying E2 here, alpha 2 here. So okay, so you're saying you could get extension.
Yes, that's one. Could you get?
Yes, but I would argue that you could also get extension out of beam E1 just by heating beam E1 up by itself. So why wouldn't you?
No, I'm thinking that there could be a situation where you would have to have this configuration if you're also including other devices, or say you can't just have a lone beam on its own. but you had to be some section underneath it. Well, okay, if I put another section on top of the same properties, then I can still get extension.
I still don't understand why you wouldn't just do extension with just the beam itself.
I was wondering if you could do it.
I don't see why you couldn't, but that seems like a very costly fabrication process. The reason why I say that is because, well, so let me think about how I'm gonna put this.
Essentially, it's-
To me, a process like that would involve bulk micro machining so that you had access to both sides of the beam suspended in free space so that you could deposit the second material on both sides of it. I'm struggling to wrap my head around how you would practically form a structure like this using a surface micro machining process where you only have access to effectively the top side of the wafer. So that you would have to lay down your high coefficient of thermal expansion material, build up a structure, filling in whatever gap you have and all of that kind of stuff to be able to lay down your beam structure, etch away everything except what you want, and then put your high coefficient of thermal expansion on top as well to make that sandwich. Seems like a costly and intensive process. So in theory, you should just get an extension out, because any bending in the up direction is going to be canceled out by bending in the down direction, assuming that your layers of material 2 are perfectly identical. If they are not perfectly identical, then you're going to have some small amount of bending in one of the other directions. So fundamentally, you should get extension, but I would argue that if you're just trying to get extension, one material and just heat it up, that's exactly what's going to happen, which is what we're about to talk about. So it could bend on its own. Like, are you saying the weight of it would be sufficient?
We are not anchoring out with other layers. As in this case, if you are only keeping this one layer and hitting it, it can bend also along with the elongation.
But so the not under uniform heating though. It'll bend under uniform heating?
It can bend because of the self-weight and all.
I don't know enough about mechanical engineering, so I'm gonna trust you on that one. I'm gonna be lazy and call it, we're looking at one axis of things. I'm a dumb electrical engineer. So that would make sense, but to me, you know, if the mass of it were enough to cause it to, if the mass were enough to overcome the spring constant and cause it to droop, you would have cantilever bending. I don't understand how the thermal heating would cause bending. I can happily look into it, so, but I'm just gonna trust you that you say it works. You seem like a smart fellow to me. So thermal actuators using a single material. Okay. So let's say that we have a beam, single beam, having Young's modulus E1 and alpha coefficient of thermal expansion alpha 1, right? If we subjected this beam to some change in temperature, we would expect that the length of the beam, the length, would increase to L plus some change in length, which would simply be L times 1 plus alpha times the change in temperature. Right? Okay. So effectively, we are inducing some thermal strain here. Let's call it in the X direction. That is alpha times delta T. Okay. So what if we had a similar situation, but now we constrain our beam on both sides so that it's anchored, right? So because the material isn't allowed to expand, the total strain has to be 0. And so we can say that our strain along our longitudinal axis is going to be alpha times delta T. So that's our thermal strain minus our mechanical strain, which tells us that our stress is negative E alpha times our change in temperature, right? Where we have a negative stress because we're in compression. Okay. Well, we can relate the stress to the force, right? So the force that's being generated by heating this beam, some amount delta T, is just the cross-sectional area of the beam times the stress. And let's throw absolute value signs here so we can get rid of this negative sign. So this is the restorative force on the boundaries. E A alpha times delta T. So what we would see effectively is that heating up a material like this is capable of generating large forces, but relatively small displacements. And the small displacement is because the coefficient of thermal expansion is usually on the order of parts per million per degree C. So what I mean by parts per million is, so if 25 parts per million per degree C is a factor of 0.00000025 change in length per, that's relative change in length per degrees Celsius. So we get very small displacements by just expanding a single material like this, right? If we wanted large expansion, we would have to use a material with a large coefficient of thermal expansion. But we can use leverage to cheat the system a little bit, okay? So what if we had an actuator like this? So we have an anchor point over here and an anchor point here. And let's exaggerate things a little bit. Say that we have this shape. So this is what's called either a bent beam actuator or a chevron actuator. Okay. So we have some nominal length here, L naught, same on both sides. This distance is X. And this distance is Y naught. So what would happen if we passed a current through this beam, effectively treating it as a resistive heater, right? This beam would generate a force in this direction as it tries to extend. This beam would generate a force in this direction as it tries to extend. And we're going to wind up having some net displacement delta y in the up direction. Fundamentally makes sense. These two things expand, it's going to force that center point outwards, right? So how much displacement should we expect to get? Let's use Pythagorean's theorem and figure things out here, right? So our change in length of either of these chevron arms is going to be the strain in the arm times the original length of the arm, or alpha delta t times the original length of the arm, right? So before we heat this thing up, we have the relationship that L naught squared is equal to x squared plus y naught squared, right? From this, we can see that x squared is equal to L naught squared minus y naught squared. After we heat this guy up, we're going to have L naught plus delta L squared will be equal to x squared plus y naught plus delta y squared. So I'm just going to expand this out. So we're going to have L naught squared plus delta L times L naught. Actually, that should be twice delta L times L naught, right? Plus delta L squared will be equal to x squared, but our x value doesn't change. So x squared is simply L naught squared minus y naught squared. And then we're going to expand out y naught plus delta y quantity squared, which is going to give us y naught squared plus twice delta y times y naught plus delta y squared. So from the jump, this minus y naught squared and this y naught squared cancel each other out. The L naught squared here on the right hand side cancels out the L naught squared here on the left hand side. And what we're going to do is we're going to say that this term and this term are going to be neglected because they're going to be really small. So we have twice delta L L naught will be approximately equal to twice delta y times y naught, which we can rearrange and say that our vertical displacement delta y will be approximately equal to L naught over y naught times our change in length. So effectively, this configuration amplifies the extension that we would see. And the gain of the system, or the amount that it amplifies, is simply the ratio of the initial length divided by the initial y value. So we can get pretty large displacements if we have long legs of our chevron actuator. Okay, So that's a pretty classical actuator that's used for in-plane displacements and the supporting math and all that kind of good stuff. Now let's talk about two more that have been used recently, and I don't have any math for them, so we're just going to talk our way through it. Okay. So these, excuse me, are going to be asymmetric actuators. So let's say that I have this situation. So here's an anchor. And then I have beam like so. Let's make this wider so that it's harder to bend. And we pass some current I through this structure. Okay. So what do we think is going to happen?
This beam is kind of bent toward the shorter side.
Towards the shorter side. So our displacement would be generated in this direction. Why do you think that? You're correct.
Because the strain created from the temperature increase would be proportional between the two beams. And since the longer beam is, well, longer, the strain creates a bigger change in length for it.
You're probably right. You're using too many mechanical engineering concepts for my peon electrical engineering brain to understand. So let me explain how my head makes it work. The length of the long leg is going to give us a larger thermal resistance because thermal resistance is proportional to length. If the same current is flowing through both legs, that means the long leg is going to experience a larger temperature change. That larger temperature change means a larger elongation. And so we have long elongation, small elongation. It's going to cause it to bend in the exact direction that you indicated. Again, using my peon electrical engineering perspective on figuring out how this thing is going to work. If it's carrying the same current and the longer leg has a larger resistance, which it has to because it's longer, then it will heat up more. Let's look at a different one. Passing constant current through both legs. What's going to happen here? Moving to the left. Why?
Because that will be having smaller thickness, so it will elongate more.
So let's call this so I can talk about things. That should be hot. I'm mixing hot and cold together and saying it's the hold arm. That doesn't work at all. So this is what we're going to call the hot arm. And this is what we're going to call the cold arm. Obviously, heat transfer occurs from hot to cold, so that it's giving us some indication here. The cold arm has a larger cross-sectional area, right, than the hot arm, which means it will heat up less. So the hot arm will heat up more because it has a smaller cross-sectional area than the cold arm. And then we have effectively the same bending concept we had earlier, right? So these are asymmetrical actuators generating planar movement using a single material. All right, that's all I had. Yep, that's it. We're done talking about thermal actuation. And I have stuff to do, as you guys do as well, so. So, your take-home portion of your exam is due tonight at midnight, I think, if you haven't already turned it in. I have on my to-do list in my office, to get you guys homework sets on all of the actuation schemes that we've talked about over the last couple of days. Last several class meetings, actually. So I'm going to hit you with a lot of homework assignments. They're not all going to be due at the same time or anything like that. Stephen, I know you're going to hate this because I did it to you last quarter and you very rightfully complained about it, but I'm thinking about making them all just due at the end of the quarter so that you can handle them at your own pace. I know I'm a raging jerk. I was full of energy at the beginning of the quarter and on top of stuff, and I am very much not right now. I sincerely apologize. I really do appreciate your feedback, and I feel like a total jerk, but that's what's going to happen. Just so that it's not a homework due every damn day while we catch up or something like this. So I really do appreciate the feedback. I feel like such a jackass, but it's what's going to happen just for my sanity and hopefully yours to some extent as well. I would encourage you all to not put off doing them until the end of the quarter. In order to facilitate you doing them in a timely or more timely fashion, I'm going to make sure that I get all of our videos and all that kind of stuff caught up and uploaded as well. And then I will associate the homework sets with the particular videos and those class meetings and all that kind of jazz. So, all right, that is enough ranting out of me for the day.